centuries, we thought light moved instantaneously, like magic. But then, in the 1600s, a curious astronomer spotted something strange through his telescope. What he discovered didn't just reveal light's speed, it rewrote the rules of the universe. Are you ready to find out why light is the cosmic speed trap? Why light's speed was once a mystery? For thousands of years, light was a mystery wrapped in plain sight. It illuminated the world, but no one stopped to wonder whether it had a speed or if it even moved at all. Ancient thinkers, like the philosopher Aristotle, believed that light's travel was instantaneous. To them, it wasn't something that behaved like sound or an arrow slicing through the air. Instead, light just seemed to be there as though it had no starting point or destination. For most people back then, this idea wasn't just reasonable, it was obvious. You light a fire and the darkness disappears. No waiting, no travel. What else could it mean but that light is everywhere all at once? But not everyone was satisfied with this assumption. Some philosophers began to toy with the idea that light might indeed have a finite speed, even if it was far too fast to be measured. An early attempt to explore this came from Empedocles, a Greek thinker who lived centuries before Aristotle. He suggested that light had to travel, and therefore must take some time to cross space. This was a bold claim for the time, but it lacked evidence, and Aristotle's view carried the day. It's hard to blame anyone for siding with him, though. After all, how could anyone possibly measure something so quick that it seemed essentially instant? To make matters harder for those early thinkers, they had little to work with in terms of tools or methods. Think about the things that are easy for us to measure. Footsteps, falling objects, even sound. Each of these produces visible or audible effects that our senses can catch. Light, on the other hand, doesn't leave an obvious breadcrumb trail. It doesn't wait for you to react, it simply arrives. Human reflexes alone stand no chance of timing it. After all, the blink of an eye lasts a full 1/10 of a second. But a beam of light can circle the Earth 7 times in that brief frame. It wasn't just the tools that were missing. The very mindset surrounding light was a barrier. Much of early science relied on what's called intuitive reasoning, drawing conclusions based on how things appear rather than testing how they work. To people relying on intuition, light's behavior didn't suggest movement, it suggested presence. And without a clear reason to challenge this assumption, the question of light's speed remained in the background, largely untouched. Still, every now and then, cracks appeared in the ancient certainty. Some began proposing a more testable idea. If light had a speed, however fast, it should take time to reach us from faraway objects, like the sun. This thought experiment puzzled even great minds like Aristotle, who reasoned that the sun's illumination couldn't be delayed because its effects were too immediate. Yet Aristotle's argument, logical as it might have seemed at the time, overlooked an important complication. How could anyone even recognize such a delay without a way to measure it? For centuries, the limits of human technology reinforced this puzzle. You couldn't just stopwatch a ray of sunlight the way you might time a sprinter. And clocks, those primitive, inconsistent timekeepers, weren't nearly precise enough to help. Plus, where would you aim them? By the time an early scholar might have managed to think up a test, they hit the same wall. Light was everywhere they looked, and would not slow down enough to be caught in the act. What changed all of this was curiosity mixed with a little stubbornness during the Renaissance. Thinkers of the time began to question even the ideas that had felt untouchable for centuries. Galileo Galilei, who we'll visit shortly, was one of these bold challengers. But before Galileo's time, thinkers were moving beyond pure observation inventing tools and refocusing science on experiments. This shift made it possible to imagine studying light as something physical rather than mysterious or divine. Another hallmark of this growing curiosity, the belief that even seemingly impossible mysteries, like light's speed, deserved investigation. By the late 1500s, discussions around topics like astronomy, optics, and motion were creating a quiet build-up to one of the first significant attempts to measure light. What's interesting is that none of these early researchers could have imagined the consequences their curiosity would spark. For them, understanding the speed of light wasn't about unraveling the universe. It was about answering a practical question. Does light actually move? This was the spirit that influenced Galileo. The Italian physicist and astronomer was a champion of turning thought experiments into real-world tests. Around 1638, he proposed a cleverly simple way to measure light's speed. While we'll dive into the details soon, his approach showed just how far humanity had come from those earlier philosophical musings. Light was no longer being considered beyond comprehension. It was being engaged with as an everyday phenomenon. Still, it's worth noting that even Galileo likely struggled with how impossible his task seemed. How do you catch something so fast it outraces not just sound, but your ability to notice it? This was the question that loomed over For now, let's stay with Galileo's moment in history. His attempts, as flawed as they were, signaled an important cultural and intellectual shift. The static confidence of Aristotle's moment, where light was either instantaneous or eternal, had given way to an era of investigating the unknown. Light had gone from being an object of philosophy to becoming a subject for hands-on study. The transition wasn't immediate, and it wasn't complete in Galileo's lifetime, but it set the stage for the discoveries to come. In the end, curiosity trumped centuries of assumption. From here, the story of light shifts into one of perseverance and ingenuity, qualities that would eventually lead a humble astronomer named Oleroma to redefine how we think about the universe. First, though, let's pause at Galileo's lantern-lit experiment, an effort that, despite its failure, reminds us how determination can lay the groundwork for discovery. Galileo's experiment to measure the speed of light begins like the kind of story you'd expect from the Renaissance. A man with a question, a lantern, and a companion standing on a distant hill. Simple, clever, and entirely doomed to fail. Armed with the tools of his time, lanterns and human eyesight, Galileo worked within the limits of his era's technology. Still, for all its limitations, his 1638 experiment wasn't just a leap. It was a signal to the world that light wasn't as untouchable as it seemed. Here's how it worked. Galileo and an assistant would each hold a lantern, their candles carefully shielded by covers that could be opened and closed. They took their positions on hilltops about a mile apart. Galileo opened the cover of his lantern, letting its light beam toward his assistant. When the assistant saw the signal, they would uncover their own lantern, sending a return signal back toward Galileo. All Galileo had to do was record the time between uncovering his lantern and seeing the assistant's flash in return. At first glance, it seemed like a brilliant and practical solution. With a known distance and the ability to measure time using the era's relatively primitive clocks, it should have been possible to calculate how long the light took to complete its trip. Divide the distance by the time and voila, the speed of light revealed at last. But as you might have already guessed, Galileo's attempt hit a wall that no amount of precision timing could overcome. The problem wasn't in the setup, it was in the phenomenon itself. The speed of light was simply far too quick to leave room for any detectable delay. Here's the issue in numbers. The speed of light is about 300,000 kilometers per second, or almost 186,000 miles per second. At that astonishing pace, light would travel a mile between Galileo and his assistant, and then another mile back, faster than their eyes or hands could respond. Human reaction time is at best around a quarter of a second. That's already longer than it would take light to complete its entire journey. In fact, the time it takes light to travel 1 mile is a fraction of a millisecond, a duration so brief it's nearly impossible for the human brain to process without help from modern technology. Galileo's clocks, which relied on pendulums or other crude mechanisms, weren't remotely capable of tracking something happening that quickly. So when Galileo saw no measurable delay between sending and receiving the light signal, he was left with only one conclusion. Either light was instantaneous, as Aristotle had claimed, or it moved too fast for his equipment and his reflexes to capture. But let's pause here for a moment. Galileo's experiment often gets remembered as a failure, when in reality, it demonstrates a kind of brilliance that's easy to overlook. For centuries, philosophers debated the nature of light, yet not one of them had attempted what Galileo did. He didn't just speculate, he set up a controlled test. That alone was groundbreaking. Even though his methods weren't enough to answer the question, his curiosity shifted the conversation from "can we think about light as instantaneous?" to "how can we prove it's not?" Imagine Galileo standing on that hilltop, lantern raised, staring into the distance. It might seem almost comical to us now, given what we know about light speed, but in that moment, he wasn't concerned about looking foolish. His experiment was rooted in a desire to test the limits of human understanding, and this attitude paved the way for the breakthroughs that followed. Even more importantly, Galileo's work planted a seed. If his experiment proved anything, it was that measuring light speed required tools and techniques far beyond what his age could provide. It wasn't possible to gauge those infinitesimally small intervals with lanterns and reaction times alone. Yet his attempt marked the beginning of a new worldview, one where light wasn't just something we saw, but something that moved, traveled, and behaved according to physical laws. This willingness to step into the unknown made Galileo's lantern experiment an important moment in the story of science. While he couldn't measure light's speed, he did something just as crucial. He proved that the question was worth pursuing.
Interestingly, Galileo might not have fully appreciated the implications of his findings. When he saw no detectable lag in his experiment, he concluded that if light did move, it was far too fast to be measured with his tools. This defeat, if we can call it that, wasn't a failure in the scientific sense. Galileo's acknowledgement of light's immeasurable speed underscored the vast gap between human capabilities and the nature of light itself. That realization might seem humbling, but for scientists, it's the kind of insight that inspires progress. After all, identifying the limits of what's possible today is often the first step toward breakthroughs tomorrow. One key takeaway here is that Galileo's experiment didn't just represent a single attempt to measure light, it marked a shift in how humanity approached the unknown. No longer were questions about light confined to the realm of speculation and debate. Galileo's hilltop lantern symbolized a shift toward empirical testing. His method may seem simplistic to us now, but in his time it was revolutionary. Yet despite his creativity, Galileo couldn't escape the fundamental challenge of his experiment. The tools he used simply weren't capable of capturing light's true swiftness. Measuring something so fast over such a short distance was beyond the reach of 17th century technology. For Galileo, The gaps in his understanding weren't failings so much as reminders of how much more there was to learn. What followed in the decades after Galileo's time was a continued effort to chase that elusive measurement. But the key to success wouldn't lie in lanterns or hilltops. Instead, it would come from an entirely different direction, one that had more to do with celestial mechanics than human reflexes. And this brings us to a Danish astronomer named Ole Rømer, who wasn't trying to measure light at all. He was simply watching moons orbit Jupiter when he stumbled upon one of the most extraordinary discoveries in the history of science. Galileo may not have captured light's speed, but his experiment remains an enduring example of scientific determination. It was a statement that even the fastest, most enigmatic phenomena were not beyond the inquiry of curious minds. Though his hilltop measurements provided no definitive answers, they shaped the questions that would eventually lead to understanding. And it reminds us, as all good science does, that sometimes our tools, and even our senses, can't keep up with the universe's pace.
The accidental discovery of light's speed. In 1676, Ole Rømer, a Danish astronomer, wasn't looking for a way to measure the speed of light. Instead, his telescope was turned toward Jupiter, where he observed one of its moons, Io, as it went about its regular orbit. Io, like a celestial timepiece, disappeared behind Jupiter at predictable intervals, its eclipses following a rhythm that could almost be set to a clock. At least, that's how it seemed. Until Rømer noticed something odd. The timing of Io's appearances wasn't as predictable as everyone had assumed. Sometimes the moon reappeared late, and other times it seemed early. It was a tiny irregularity, almost small enough to ignore, but Rømer paid attention. What started as a curious question about Jupiter's moon would unexpectedly reveal something much larger, a clue that light didn't move instantly after all. So, what exactly was Rømer seeing? Io orbits Jupiter swiftly, completing a full lap every 42.5 hours. From Earth, this means observers can watch it dip behind Jupiter, disappearing into shadow like clockwork. But as Rømer closely tracked these eclipses, he noticed that the timing wasn't constant. When Earth and Jupiter were moving closer together in their orbits, Io seemed to appear earlier than expected. When Earth and Jupiter drifted farther apart, Io's reappearance lagged behind schedule, as if the light carrying the image of the moon was arriving late. This subtle yet persistent inconsistency was perplexing. If Io's orbit was so regular, why weren't the eclipses lining up? At first, it wasn't clear what could cause such a variation. Maybe Io's orbit itself was somehow changing, wobbling unpredictably. But to Rømer, this didn't quite add up. Jupiter's gravity was steady and strong. There was no reason to suspect Io's path was fluctuating in a way that would explain these timing shifts. So Rømer dug deeper, piecing together an explanation that no one had seen before. What if the delay wasn't about Io at all? What if it was about the time it took light to make the journey from Jupiter to Earth? Rømer began to suspect that the changing distance between Earth and Jupiter was the key. As both planets followed their elliptical orbits around the Sun, their separation varied, sometimes growing closer, sometimes farther apart. When Earth was closer to Jupiter, the light reflecting off Io had a shorter distance to travel. When Earth moved to the far side of its orbit, that light had to cross a much greater distance, and that extra travel time created a small but measurable delay in the observed eclipses. In other words, the irregular timing wasn't a problem with Io's orbit. It was evidence that light didn't move instantaneously. For Rømer, this was a breakthrough. Light, he realized, took time to travel.
To understand the scale Rømer was working with, consider the vast distances involved. At its closest point, Earth is still hundreds of millions of miles from Jupiter. Even light, which moves unimaginably fast, needs time to cover that distance. This realization was completely at odds with what most people believed in Romer's time. The long-held view, shaped by Aristotle and carried forward into the modern era, was that light traveled instantly. It seems so obvious. When you light a candle, the room brightens immediately. Why would anyone think otherwise? But Romer's observations of Io told a different story. The speed of light, though incredibly quick, wasn't infinite. It was finite, measurable, and for the first time, evidently real. Using his observations, Romer even attempted to quantify light's speed, a staggering challenge given the tools available in the 17th century. He estimated that it took light about 22 minutes to cross the span of Earth's orbital diameter, a distance of roughly 186 million miles. From this, he arrived at an approximate speed for light, calculated at around 220,000 kilometers per second. It wasn't perfect. Modern measurements place the actual value at about 300,000 kilometers per second. But it was remarkably close, especially considering the challenges Romer faced. Without precise clocks or accurate knowledge of the distances involved, his result was an extraordinary achievement, and it marked the first time light speed had ever been successfully estimated. Romer's discovery was revolutionary, but it wasn't immediately embraced. The idea that light moved at a finite speed challenged centuries of scientific thought. Even after Romer presented his findings in Paris, where he was working at the Royal Observatory, some of his contemporaries remained skeptical. It wasn't until much later, when other experiments confirmed his conclusions, that the world fully accepted the implications of his work. Romer had essentially cracked open a door to a new understanding of the universe. Light, once thought to be almost mystical in its nature, was now understood to obey physical laws, just like everything else. What's fascinating about Romer's breakthrough is how accidental it was. He hadn't set out to study light at all. His focus was on astronomy, and his observations of Io were meant to refine our understanding of the Jovian system, not to question the nature of light itself. And yet, by paying attention to those subtle discrepancies, those tiny delays of mere minutes, Romer uncovered one of the most profound truths about the physical world. Some discoveries, it seems, hide in plain sight, waiting for someone curious enough to notice them.
Of course, Romer's methods weren't perfect, and his estimates had limitations. Part of the challenge was the technology of his time. Clocks in the 17th century weren't precise enough to measure very small intervals with high accuracy, and the exact distances between celestial bodies weren't yet known. Even so, Romer's ability to arrive at a reasonable estimate for light speed with such limited tools speaks to his ingenuity. His work laid the foundation for more accurate measurements in the centuries to come, proving that even small insights can ripple outward into big discoveries. There's something poetic about the way Romer's findings came to light. Literally, the same phenomenon that illuminated Jupiter and Io ultimately illuminated the nature of light itself. Romer showed that the universe is a place of connections, where one observation can quietly unlock a larger truth. Light, which we so often take for granted in its speed and reliability, turned out to be a carrier of something unexpected: time itself. The delay Romer found wasn't just a curiosity, it was a signpost pointing toward a deeper understanding of how light and space interact. Romer's discovery is often seen as a stepping stone to later work, like the experiments of Hippolyte Fizeau and Léon Foucault, who refined measurements of light speed with rotating mirrors and precise timing devices. But it's important to give Romer his due. His realization that the universe's distances are vast enough to make light pause along the way was a transformative leap. It reminded us that even the quickest thing in existence is still bound by the laws of motion and time. Most importantly, Romer's work changed more than the numbers on a chalkboard.
It invited us to reconsider what we thought we knew about the universe. If light wasn't instantaneous, what else might work in ways we hadn't noticed yet? The journey to understand light didn't end with Römer, but his contribution marked a turning point. It showed that the questions worth asking aren't always the ones we set out to answer, and that sometimes the most profound truths are discovered by accident. As we step away from Römer's story, let's turn to the next phase of light's journey. With new tools and an even greater drive to measure the seemingly immeasurable, scientists in the 19th century would push the boundaries even further. Römer had shown that light wasn't infinite, but it was left to others to find just how fast it really was. That's where we're headed next.
Watching light with rotating wheels and mirrors. Measuring the speed of light is like trying to catch a gust of wind in your hands. It's always faster and harder to grasp than it seems. But in the mid-1800s, a French physicist named Hippolyte Fizeau crafted an experiment that finally rose to the challenge. It didn't involve celestial moons or staggering distances, though. His solution was much closer to home and surprisingly down to earth. A toothed wheel, a light beam, and a mirror. That was it. This experiment would become the first terrestrial measurement of light speed and change how we understood one of nature's fastest phenomena. Here's how it worked. Fizeau set up a contraption where he positioned a rotating wheel with evenly spaced teeth alongside a beam of light. The light was sent streaming through one of the gaps between the teeth and aimed at a mirror several miles away. This mirror then reflected the beam straight back toward the wheel. Here's where it got clever. As the wheel spun faster, the returning light wouldn't line up with the same gap it passed through earlier. Instead, it would hit a tooth and get blocked. By adjusting the rotation speed of the wheel just right, Fizeau determined the exact moment when the light could no longer return to his eyes. To figure out the speed of light, Fizeau needed two essential pieces of information: the distance between the wheel and the mirror, and the speed at which the wheel was rotating. With the distance set and the precise timing of the wheel's rotation accounted for, Fizeau could calculate how long it took for the light to make its trip to the mirror and back. This gave him a direct way to estimate the speed of light. But let's stop and appreciate how remarkable this setup really was. Remember, light moves at nearly 300,000 kilometers per second. It races so quickly that you'd barely notice it moving, even if you could see it travel across short distances. And yet, Fizeau found a way to slice this immeasurable speed into pieces small enough to study. The toothed wheel acted like a timing gate, breaking light's journey into manageable intervals, almost like placing a stopwatch on something that finishes its lap in less than a blink. Without high-tech tools, Fizeau's experiment relied on ingenuity in its simplest form. What makes this even more impressive is how close Fizeau's results were to the modern value for light speed. Using this method, he calculated light speed to be about 193,000 miles per second, a bit slower than the number we use today, but remarkably accurate given his equipment. For the first time, someone on Earth had Fizeau's experiment also carried a deeper significance. It was a turning point where measuring light speed stopped being something only astronomers could attempt using the cosmos as their measuring stick. Here on Earth, anyone with the right setup could recreate the experiment. That wasn't just a scientific move forward. It was an opening of doors. Suddenly, the idea of measuring light speed transformed from something reserved for the heavens into a human-scale challenge. Fizeau's setup was brilliant,
But as science often proves, there's always room for more precision. Enter Léon Foucault, another French physicist, who stepped in to refine the method. Foucault took Fizeau's idea and made one simple yet transformative swap. Instead of a toothed wheel, he used rotating mirrors. This change wasn't just about improving accuracy, it was about revolutionizing how measurements could be made altogether. Here's how it worked. Foucault's device used a system of mirrors, one of which was rapidly spinning. A beam of light would bounce off the first mirror, travel to another stationary mirror placed farther away, and then return to the spinning one. But because the spinning mirror moved slightly during the light's journey, the returning beam didn't hit the same spot it started from. Instead, it shifted very slightly. This displacement wasn't random. It depended directly on how fast the light traveled and how quickly the mirror rotated. By carefully measuring the shift and knowing the distances involved, Foucault could calculate light speed with even greater precision than Fizeau. Foucault's adjustments not only refined the earlier measurement, but also revealed something else that would ripple through the scientific world. During his experiments, he also tested light traveling through water instead of air. To his surprise, and perhaps to no one's relief, he confirmed that light slowed down in water. It wasn't dramatic, but it was enough to notice. This might sound small, but it was a powerful confirmation of ideas about how light behaves and interacts with different materials. It also lent strong support to the wave theory of light, which argued that light behaves like a wave rather than particles racing through empty space. Think about this for a second. Foucault's rotating mirrors didn't just refine an already astonishing measurement. They also quietly answered fundamental questions about the nature of light itself. Was it something that simply moved in a straight, uninterrupted line, indifferent to what it passed through? Or was it something that adapted, changing its behavior based on its surroundings? Foucault's measurements proved the latter. Light wasn't untouchable. It interacted, it slowed down, it followed rules. With this new technique, Foucault's results brought the speed of light's measurement to within 1% of today's accepted value. For comparison, Fizeau's numbers had been impressive for their time, but Foucault's improvements shaved off uncertainties and brought the margin of error far closer to zero. These two experiments, only a few years apart, showed just how rapid scientific progress could be when creativity and persistence joined forces. What might be the most remarkable aspect of both Fizeau's and Foucault's work is how straightforward the principle was. Neither relied on otherworldly tools or impossible conditions. They used gears, mirrors, light beams, and a lot of patience. But it's their imaginations, their ability to turn ordinary materials into extraordinary experiments that made all the difference. Once again, light's speed stopped being untouchable. It moved out of the realm of distant stars and moons and into everyday labs. It became part of the world we could quantify, measure, and understand. But, as is often the case in science, every new answer brings new questions. If light's speed was now measurable, what exactly determined this value? Why wasn't it slightly slower or impossibly faster? And more importantly, could anything exceed it? These weren't just idle questions. They were fundamental challenges that would eventually steer scientists toward an even deeper understanding of how light reveals the structure of the entire universe. Fizeau and Foucault weren't just pioneers in their own right. Their designs and discoveries built the bridge between early ideas about light and the revolutions that followed. Every spinning mirror and every carefully adjusted wheel was another reminder that even nature's fastest traveler wasn't above being clocked. But why does light move at this speed, no slower and no faster? And how is it tied to the very fabric of reality itself? This was a question that scientists like James Clerk Maxwell were beginning to ask, leading to something far more powerful than just numbers. The realization that light carried the blueprint of nature's deepest laws. That's where we're headed next. Maxwell's equations. The blueprint of light. What if the speed of light isn't just a number we measure, but something fundamental, stitched into the very rules that make the universe work? To understand why this discovery was so revolutionary, let's back up and talk about what Maxwell's equations actually described. In essence, his work showed how electric fields and magnetic fields interact and feed into one another. Picture this. Whenever you wiggle a charged particle, it creates a ripple in the electric field around it. That ripple, in turn, generates a magnetic field, and as that magnetic field changes, it loops back to produce a new electric field. Together, these two fields can sustain each other, passing energy back and forth as they move through space. What Maxwell discovered was that this dance between electric and magnetic fields could create waves. Waves that required no physical medium, meaning they could travel through the emptiness of a vacuum. And here's where things get interesting. Maxwell's math didn't just predict the existence of these electromagnetic waves. When he crunched the numbers, the equations also revealed that the waves would move at a very specific speed. That speed turned out to be roughly 300,000 kilometers per second, essentially identical to the best measurements of light's speed at the time. This wasn't a coincidence. What Maxwell had uncovered was the true nature of light. It wasn't some mysterious, unique phenomenon. It was an electromagnetic wave, just like the ones described by his equations. In a single leap, light was no longer something unknowable. It had become a part of the larger story of electric and magnetic forces. But why does light have a fixed speed? In Maxwell's equations, the answer emerges naturally. The speed of electromagnetic waves comes from two constants of nature. One that describes how electric fields behave in a vacuum, and another for magnetic fields. These constants are woven into the very fabric of Maxwell's equations, and when combined, they dictate how fast electromagnetic waves, light, must travel. To put it simply, the speed of light isn't arbitrary or up for discussion. It's baked into the basic rules that describe how the universe works. If electric and magnetic fields exist, light has no choice but to move at the speed set by these constants. There's a fascinating beauty in this discovery. It means the speed of light isn't just a property of light itself. It's a reflection of something deeper. Maxwell's equations showed that light's speed emerges from the structure of the universe, a kind of cosmic consequence of the way electromagnetic forces behave. If you tried to imagine an alternate universe with different properties, you'd still end up with electromagnetic waves moving at a speed dictated by whatever the new constants were. It's unavoidable, part of the immutable laws that shape reality. Maxwell's work didn't only reveal the electromagnetic nature of light. It also introduced the idea that light's speed might be a sort of universal speed limit. After all, if this constant was dictated by the laws of physics themselves, it wasn't something that could be broken or adjusted. This wasn't just a quirky footnote in his equations. It was a profound statement about the world. At the time, though, most people didn't fully appreciate the implications of this discovery. To them, light's speed seemed like more of an interesting fact than a fundamental constraint on nature. But it didn't take long for scientists to start asking deeper questions. If light traveled at a fixed speed, what did that imply about space and time? Was this constant speed the same for everyone, no matter how they moved? And more unsettlingly, what did it mean for objects that might try to exceed that speed? Maxwell's equations hinted at answers, but they left room for more exploration. Maxwell's math also highlighted something subtle but profound about the universe. Electromagnetic waves like light don't need a medium to travel through. Imagine sound waves. They need air or some other substance to move, which is why outer space is silent. But light doesn't need anything. It propagates through the vacuum of space all on its own, carried forward by the interplay of electric and magnetic fields. This was another groundbreaking insight. For centuries, scientists had debated whether light needed some invisible substance, often called the luminiferous ether, to carry it through space. Maxwell's work suggested that no such ether was necessary. Light was self-sufficient, a traveler that brought its own rules along for the ride. But Maxwell's equations didn't just explain what light was or how fast it moved. They also raised new and unsettling questions about the nature of space-time itself. The fact that light moved at a constant speed, independent of its surroundings, defied the way most people thought about motion back then. For centuries, physics had been dominated by the ideas of Isaac Newton, which treated space and time as absolute. If you were moving toward a beam of light, Newtonian logic suggested that you should observe it arriving faster than if you were standing still. But Maxwell's equations left no room for this. Light always moved at the same speed, no matter who was observing it or how they were moving. This apparent contradiction puzzled scientists for decades. How could the speed of light remain constant, regardless of the observer? What did that even mean for motion, time, and distance? These questions would linger until the early 20th century, when Albert Einstein built on Maxwell's foundation to answer them with his theory of relativity. But even before Einstein, Maxwell's insights were revolutionizing science. By unifying light, electricity, and magnetism, he didn't just provide an explanation for the speed of light. He challenged humanity's understanding of the physical world. For the first time, light was seen not as something unique or separate from other forces, but as a part of the larger interconnected framework of nature. Everything from the glow of a candle to the deep red light of a sunset now had a common explanation. They were all electromagnetic waves, obeying the same laws and traveling at the same cosmic speed. Maxwell's equations also hinted at new possibilities. If light was just one kind of electromagnetic wave, could there be others? And indeed, there are. His equations paved the way for the discovery of radio waves, X-rays, and more, different forms of electromagnetic radiation that vary only in their wavelength and frequency. Every beam of light, every radio signal, and every X-ray pulse is part of this diverse electromagnetic spectrum, all traveling at the same fundamental speed. Maxwell's insights didn't just explain the natural world. They expanded it, showing us phenomena we hadn't even known existed. Even now, Maxwell's equations,
remain one of the most elegant achievements in science. They describe the behavior of electric and magnetic fields with such clarity that their implications ripple far beyond their original context. When you follow the threads of his work, it's easy to see how it prepared the groundwork for Einstein's theories. Maxwell showed that the speed of light wasn't just a measurement, it was a constant, an inescapable feature of the universe itself. And if light's speed was so deeply tied to the laws of electromagnetism, then space and time, the stage on which everything occurs, must also be shaped by those same laws. The transition from Maxwell to Einstein wasn't a sharp break, but a continuation, like stepping from one level of understanding to the next. Maxwell gave us the blueprint of light, how it moves, what it's made of, and why it travels as it does. But the deeper question still lingered. What does this constant speed mean for the universe we live in? To answer that question, we need to look at what happens when you treat light's constant speed not just as a number, but as an unbreakable rule. Einstein asked that very question, and the answers he found changed everything. Einstein's cosmic speed limit. Albert Einstein wasn't satisfied with just understanding the speed of light. He looked at Maxwell's equations, saw their elegance, and asked himself something much bigger. What if the speed of light isn't just a behavior of waves in space, but the universe's ultimate speed limit? What if this one constant, the rate at which light moves, governs how everything else behaves, from the smallest particles to the largest galaxies? These questions became the foundation for his special theory of relativity in 1905, and with it, Einstein transformed not just our understanding of light, but the way we think about space, time, and motion itself. At the heart of Einstein's theory is a simple yet startling idea. The speed of light in a vacuum is constant, no matter how fast you're moving or which direction you travel. Whether you're standing perfectly still, riding a train, or speeding through space in a futuristic spacecraft, you'll always measure light moving at the exact same rate, about 300,000 kilometers per second. It's hard to overstate how strange this idea is, because it defies everything we intuitively think about motion. For example, if you're running towards someone, throwing a baseball, the ball seems like it's coming at you faster than if you were standing still. Common sense says speeds should add together, but light doesn't work that way. No matter what kind of motion is involved, it won't budge from its constant speed. This one principle, light's unchanging pace, has surprising consequences. It means the way we experience time and space isn't fixed. It depends on how we're moving. If you're speeding up, nearing the speed of light, the entire framework of existence begins to bend around you in strange and dramatic ways. Consider time, for instance. Normally, we measure time in steady ticks. Seconds march forward evenly. The clock hands spin predictably. But Einstein showed this isn't always true. Imagine an astronaut traveling at 90% the speed of light. From their perspective, time aboard the spacecraft feels completely normal.
But someone watching them from Earth would see something entirely different. Time for the astronaut appears to slow down. A journey that feels like a few months for the astronaut might actually take years for the people they left behind. This effect, known as time dilation, has been proven through experiments. For example, scientists. This bending of time is only the beginning. Another consequence of special relativity is that distances shrink when you move quickly. If you're racing through space in the direction of a far-off star, the space between you and that star begins to contract. To an outside observer, it looks as though the trip is impossibly far, but to you, the star may feel close enough to touch. This effect, called length contraction, isn't something we notice in our day-to-day lives because we travel so slowly compared to light. But when speeds start to climb to a significant fraction of light's speed, space itself starts to ripple in strange new ways, folding distances into smaller pieces. Relativity doesn't stop there. Even which events happen first, or whether two events happen at the same time, depends on your motion. Imagine two lightning bolts striking opposite ends of a moving train. To someone on the platform, the bolts might seem simultaneous, but to a passenger sitting inside the train, one might appear to strike first, depending on which direction the train is moving. Both observations are equally valid, yet they contradict each other. This idea, known as the relativity of simultaneity, reveals just how closely linked space, time, and speed really are. The universe isn't rigid, it's adaptable. Its reality shaped by the motion of whoever's observing it. But perhaps the most mind-boggling fact of all is what happens when you try to push toward the speed of light. Imagine you're in a spaceship, steadily accelerating, trying to close in on 300,000 kilometers per second. At first, everything seems reasonable. You add more energy, and your speed increases as expected. But as you continue to accelerate, something strange begins to happen. The energy you're adding doesn't translate into speed the way it should. Instead, it starts making you heavier. Your mass increases as your velocity climbs, and the closer you get to the speed of light, the harder it becomes to gain speed. To reach the speed of light, you'd need an infinite amount of energy, which of course is impossible. This is why nothing with mass can ever reach or exceed the speed of light. It's not just a limitation in technology or a question of practicality. It's a law of the universe, ingrained in the fabric of space-time itself. So what makes light special? It's because photons, the particles that make up light, are massless. They don't need infinite energy because they're already traveling at the one speed the universe allows. For anything with mass, though, even something as small. Even more interestingly, this speed limit is what keeps the universe ordered. Without it, causality, the idea that causes must always happen before effects, would completely collapse. If information or energy could move faster than light, you could theoretically send a signal into the past and create paradoxes. Imagine getting a warning about something that hasn't happened yet, or receiving an answer before you've asked the question. The logical sequence of events would break down. By enforcing this universal speed limit, the fabric of space-time ensures that the universe remains consistent, with no backward loops or contradictions. At this point, light's role in the universe begins to feel almost less like a physical phenomenon and more like a rule book. Its speed defines the boundary between what's possible and what isn't, serving as the bridge between space and time. Even Einstein's famous equation, E=mc², is built around it. In this formula, the speed of light acts as the link between energy and mass, revealing a deep connection between two concepts that once seemed completely separate. It's as if light's speed isn't just the pace at which something moves, it's the scaffolding for reality itself. Understanding light's speed fundamentally changed how we think about the universe. Space, time, mass, even energy itself, they're not separate, rigid things, but part of a fluid, interconnected structure shaped by motion and speed. Special relativity showed us that these concepts are all relative, bending and stretching based on how fast you're moving. Light holds it all together, remaining constant no matter what. But light's influence doesn't stop there. By establishing this universal speed limit, Einstein opened the door to even deeper questions. If nothing could go faster than light, what did this mean for our understanding of the universe's limits? How does this constant shape large-scale structures, like galaxies, and small-scale particles, like photons? These questions would drive physics into new, unexplored territory, a journey that would take us beyond the mechanics of light itself, and into the realms of gravity, black holes, and the very curvature of space-time. The speed of light isn't just a number or a fact of nature, it's the thread that ties together everything we know about reality, from the way time flows to the limits of causality. Light isn't simply a traveler racing through the cosmos, it's a boundary, a law, and a map of the universe's deepest workings. And yet, even with its extraordinary importance, it has one more role that's worth exploring, one that connects the cosmic to the everyday. Because while light shapes the universe on an enormous scale, it also plays a surprisingly intimate role in protecting the order we experience.
Causality, how light keeps the universe in order. If light didn't have a speed limit, the universe might feel more like a house with doors swinging off their hinges. The rules we take for granted, like the idea that every cause leads to an effect, could break down in ways that are hard to wrap your head around. That's where the concept of causality steps in, and light speed is its quiet protector. Causality is the principle that every effect has a cause. You flip a switch, the light comes on. You drop a book, it falls. It's a sequence that feels so familiar, it's easy to overlook. But it's also delicate. If the speed of light could be surpassed or ignored, this orderly chain of events might unravel, tossing the logic of time into chaos. Imagine, for instance, a world where information or energy could travel faster than light. Let's say you send a message faster than this universal limit. Depending on how far it needs to go, the message could arrive almost instantaneously. Or worse, it could appear before you even sent it. That sounds odd, doesn't it? A letter arriving before it's written, or a question being answered before it's asked. These scenarios aren't just confusing. They poke holes in our concept of time itself. If effects can outrun the causes that create them, it's like undoing the threads of a story. Things happen out of order, and suddenly
nothing makes sense. This isn't just theoretical speculation. Faster-than-light communication would violate one of the universe's most essential principles, that time flows in a single direction. If messages could outpace light, they'd essentially move backward in time, creating the potential for paradoxes. Picture this. You send a warning to your past self to stop something bad from happening. If your past self listens and avoids the disaster, then there's no reason for you to send the warning in the first place. The warning would erase itself, and without it, the disaster would happen again, a never-ending loop of contradictions. These aren't the kind of paradoxes you can shrug off. They're deep enough to unpick the fabric of space-time itself. In physics, the speed of light acts like a safeguard against these logical disasters. It keeps information and energy from exceeding the boundaries that causality needs to function.
Inside the light cone, causality reigns. Events within its boundaries can influence one another, like cause and effect, patiently working together. But outside the cone, that's where things become untouchable. Events beyond this boundary exist too far away for light or anything to have reached yet. So while they're real, they're completely disconnected from the present moment. No information can travel faster than light to break into this unconnected region. This is why faster-than-light travel wouldn't just be fast, it would be disruptive. It would pierce the boundaries of light cones, mixing events together in ways that defy logic. The speed of light forms an invisible line between what's possible and what isn't, carving space-time into zones of influence. This doesn't just keep reality consistent, it ensures that the past flows into the present and onward into the future. Without this speed limit, events wouldn't be tied to a clear sequence, and time itself would lose its meaning. The speed of light turns the universe into a rule-bound structure, one where cause always precedes effect. It's hard to overstate how foundational this is. Without the speed of light acting as nature's gatekeeper, even the laws of motion and energy conservation would start to crumble. To see why this boundary matters, think about something as simple as a conversation. Right now, when you speak, your listener hears your words travel through the air at the speed of sound, far slower than light. If sound worked like light, no matter the distance, your listener would still experience that time delay. No faster-than-light cheat codes allowed. Now imagine that the universe didn't respect light's speed. What if you could shout words that reached someone across the galaxy immediately? At first it sounds convenient, but it would bring problems. Your words could arrive in bizarre orders, or worse, a reply might return before you even spoke. Messages would tangle themselves into timelines in ways that make even the simplest exchanges break down. Every moment would be disconnected, unable to build upon what came before. The logic of space-time relies on light's speed to dictate what happens when. If light didn't have a limit, causality wouldn't just bend, it would shatter. The idea that the past affects the future, but not the other way around, is part of what makes the universe stable for us. The speed of light's limit is essential for preserving this order by restricting the speed at which information can travel. It's the quiet safeguard that ensures the past stays in the past and that the future remains open to possibilities. Without it, we wouldn't just question time, we'd lose all sense of consistency. But this speed limit doesn't just enforce rules.
It defines what we can experience. Light cones aren't walls, they're maps. They tell us what's within reach and what still lies out of touch. Think of each moment as a local neighborhood of influence, shaped by the finite nature of light's travel. Events that happen outside the reach of light aren't frozen forever. They merely haven't reached your timeline yet. The beauty of this setup is that it turns light into a bridge, while guarding the structure of space-time at the same time. This connection between light and causality is why faster-than-light travel always feels like the stuff of science fiction. It's not just difficult, it's incompatible with the universe's rules. Offering an enormous cosmic speed doesn't restrict us. It holds everything together. Without this limit, reality would be a puzzle with pieces that never add up. As we zoom out to think about the broader picture, causality, a concept that sounds so philosophical, becomes something entirely practical. It's the framework that makes choices matter, allows information to flow, and keeps the timeline stable. The speed of light is its unsung hero, quietly handling the logistics behind the scenes. Even across distances we can barely fathom, from the light cones of far-off galaxies to the everyday passage of seconds here on Earth, this limit keeps everything moving forward in unison. And yet, the speed of light is more than just a cosmic rule. It's part of what connects us to each other, to the stars, and to the farthest corners of the universe. It's the reason we can trust that the sunrise will follow the night, and that our hand waves will reach the eyes of those watching. So while light speed might seem like an unyielding constraint, it's really a gift, keeping the story of the universe intact and ensuring that causes always bring their effects. And speaking of connections, there's a softer side to light speed too. It shapes everyday life in ways that feel ordinary until you pause to think about them. Everything from how our technology works to the way we see the stars. This universal speed isn't just for scientists or cosmic theorists. Whether it's bouncing between satellites to guide us home or carrying whispers across space, light's pace is woven into the fabric of modern life. It doesn't just keep the universe moving forward, it brings us closer together. Let's explore that next.